So today's class we will discuss about the PSW register, that is the flag register of 8051 microcontroller. So 805 the flag register of 8051 microcontroller, it's an 8-bit register. So it's also called program status word register. So the 8 bits are, these are the 8 bits PSW 0.0 to PSW 0.7. So each bit of the register indicates a particular flag. So it is an 8-bit register. It is also called the flag register as it mainly contains the status flag. These flags indicates the status of the current result. So they are changed by the ALU after every arithmetic or logical operation. So these after completing every ALU operation, the status flag will be updated by the ALU. So not only the ALU, the programmer can also change the status flag. So that is especially these three flags, that is F0, RS1, RS0 are the flags that is changed by the programmer. So also can change the flag can also be changed by the programmer. PSW is a bit addressable register. Bit addressable register means the individual bits can be set or reset by the programmer. So not the whole byte cannot, no need of changing the whole byte to change one bit of the register. We can access each bit individually by the programmer. So the bits can be referred to by the bit number, that is, for example, that is PSW 0.4, or by their name. So PSW 0.4, that is this bit. They can change if you want to set RS1, we can name it as set B PSW 0.4, that will set the RS1 flag, or you can represent it by the name of the flag, that is set B RS1 can also be used to set or reset the with clear instruction we can reset the particular bit. So first one is the carry flag. You can see that this is the carry flag. PSW 0.7 is the carry flag. So carry flag indicates the carry out of the MSB after any arithmetic operation. So after performing any arithmetic operation, if there is a carry out from the MSB bit, the carry flag will be set. So if carry flag is 1, there was a carry out of the MSB during the current ALU operation. So if carry flag is equal to 0, there was no carry out of the MSB bit. So we can consider an example that we have taking an example 1111 plus 00000001, that is FF plus 01. We'll get 0 with the carry 1 here. So again 0 with carry 1, 0 with carry 1, and 0 with carry 1, 0 with carry 1, 0 with carry 1, and 0 with carry 1. We get 0 with carry 1. So we have a carry out of the MSB bit. So in this case, the carry flag will be set. So this case, the carry flag will be set. So if an example, if there is no carry out from the MSB, the carry flag will be reset. The carry flag will be 0. So if we get a carry out here from the MSB bit, this is the MSB bit, we are doing a 8-bit operation. So our result also will be 8-bit. And if we are getting a carry out of the 7th bit, then this is the 0th bit and this is the 7th bit. If we are getting a carry out of the 7th bit, that is the carry out of the MSB, that is the carry. Then the carry flag will be set. If there is no carry like this, such carry, the carry flag will be 0 after the ALU or current ALU operation. So next one is the auxiliary carry. So the auxiliary carry, this is the auxiliary carry, that is PSW 0.6. So the auxiliary carry flag, indicates there is a carry from lower nibble to higher nibble. So in the previous example, if you have 8-bit number, it's a byte. 8-bit means it's a byte. So in a byte, we have 2 nibble. Lower 4 bits are called the lower nibble and the upper 4 bits are the higher nibble. So we have two nibbles in an 8-bit or in a byte operation. So this is the lower nibble and this is the higher nibble. So if there is a carry out from the lower nibble to higher nibble, that indicates an auxiliary carry. So if 8 bits are numbered bit 7 to bit 0, this is the carry from bit 3 to bit 7. So I will show the example. So AC is equal to 1, that means there was an auxiliary carry. If AC is equal to 0, there was no auxiliary carry. So taking the same example, that we are getting a carry out here. So this is the lower nibble and this is the higher nibble. So we are getting a carry out from the lower nibble to the higher nibble. So this carry is called the auxiliary carry. So we have, in this case, the auxiliary carry flag will be set after doing this operation. And if there was no such carry, the auxiliary carry will be 0. So this auxiliary carry is not taken into consideration in all situations. So it will be considered when we are doing decimal just after addition. So DAA instruction, when the DAA instruction comes. All other case, we are the carry out of the MSB is only taken into consideration. So next one is the parity flag. So it indicates the parity of the result. So after doing an ALU operation, the result will be stored in the register A. So in the parity determines the number of ones in the result. So if we are getting a result, we are checking the number of ones in the result. If it has even number of ones, that means even parity, then the parity flag will be 0. And if there is odd number of ones, that is odd parity, that is the parity flag will be 1. So you can see that here we have, I can take an example, that is, it is the result of an ALU operation, that is 11001010. So in this case, we have 4 number of ones in the result. So we have, that is even parity, that is parity flag is equal to 0. Can take another example, that is 11101001. In this case, we have 5 ones in the result. So there is odd number of ones, that means odd parity. So the parity flag is equal to 1. And the next bit, that is F0. F0 is user defined flag. So this flag is available to the programmer. The programmer can all the carry flag, auxiliary carry flag, the parity flag, and also overflow flag. These 4 flags will be set by the ALU after every ALU operation. The other 2 flags, that is F0 flag and register select flag, that is RS0 and RS1 flag, will be set by the programmer. So this flag is available to the programmer. So this flag is available to the programmer. It can be used by programmer to store any user-defined information. For example, in an air conditioning unit, programmer can use this flag to indicate whether the compressor is on or off, that is 1 or 0. So this flag can be changed by simple instructions like set B and clear instruction. So we have already discussed about set B and clear instruction. Set B means to change the bit to 1 and clear means to change the bit to 0. So if set B PSW 1.5, this makes F0 bit, the F0 flag to 1. And if we are clearing PSW 0.5, that is the bit number, PSW 0.5 is the bit number of F0 flag. This makes the F0 flag to 0. So this is the F0 flag. So this is the number PSW 0.5, that is the user defined flag. So set B instruction can be used to change it to 1, and to clear this, that is to make a 0, we can use clear instruction. The next is register bank select. So we have 128 bytes of internal RAM is available for 8051 microcontroller. So the initial 32 location, that is initial 32 bytes of internal RAM are available to the programmer as registers. So having so many registers makes the programming easy and faster. But the naming of registers, that is R0 to R31, you have 32 registers, so we can name it as R0 to R31. So the naming would tremendously increases the number of opcode. So if you're using different register, so every instruction that we will be stored in the memory as coded in a coded form. So every instruction that we are writing in assembly language, it will be converted to the coded form, that is the opcode. So this opcode will be different for different registers. When we are using different registers, or for the same instruction, if you are using different registers, the opcode will be changed. So if we can use the 32 different registers, also plus 2 registers, that is A register and B register can be used for every instruction. So this will generate so many opcodes for the same instruction. So to avoid the number, if we are using 32 register, we will get the 32 opcode for the same instruction. So to avoid that, we are using only the register name, 8 register names, that is R0 to R7. So only we are using 8 register names. So these names, so this 32 registers are divided into 4 banks. So 4 bank means bank 0 to bank 3. So each bank contains 8 registers, that is named R0 to R7. So we have 4 banks and each bank contains 8 registers. The name of the register is R0 to R7. So by reducing the 32 names to 8 names, we can reduce the opcode, 32 set of opcodes to 8 opcodes. So we will get as 8 set of opcodes for an instruction, for the same instruction. So at a time, only one of the 4 bank is active. So we have 4 banks, but only at a time only one bank will be active. Which bank is active is decided by the register bank select bits. That is RS0 and RS1 will decide which bank is active at a time. So we can see that this is PSW.4 and PSW.3, that is RS0 and RS1. So this will decide which bank will be set at a time. So we have 4 banks, so we need 2 bits to select the bank. So 00 means registers bank 0, 01 that is bank 1, 10 bank 2 and 11 is bank 3. So using these 2 bits, we can select the register bank. So here we divided the 32 registers to 4 banks, that is bank 0, bank 1, bank 2 and bank 3. That means each bank contains 8 registers. The name of the register is same in all the bank. R0 to R7 is the name of the register. But at a time only one of the bank will be selected. So which bank is selected, that is decided by the register bank select pin. So if it is 00, that means the bank 0 is selected. So to set the 00, we need to clear both the RS1 and RS0 flags. So clear PSW.0 and clear PSW.3 will clear both the flags, and the register bank 0 will be selected. And to select the register bank 1, the RS0 should be 1 and RS1 is 0. So clear PSW.4 and set B PSW.3 will select the register bank 1. So register bank 2 is 1, 0, that is RS1 is 1 and RS0 is 0, that is set B PSW.4 and clear PSW.3 will select register bank 2. And to select register bank 3, both the RS1 and RS0 is set. So set B PSW.4 and set B PSW.3 will select the register bank 3.